We think of neural networks as these all-powerful brains that can learn pretty much anything. But what happens when you ask one to do something really, really simple? Something you could solve in high school algebra. You'd expect it to be perfect, right? Well, it turns out that's not what happens at all. Today we're going to unpack this super interesting paradox, why even the smartest AI can't seem to get a simple equation exactly right.
So this is the big question, especially if you're an engineer or a data scientist. You've probably been there. You train a model, you overfit it on purpose, basically forcing it to memorize the data. The training error drops to practically zero, and yet the final output is still not quite right. It's close, sure, but in engineering, close can be the difference between a part that fits and one that doesn't. So what is going on under the hood?
Here's our game plan for today. First, we're going to lay out this perfect fit paradox. Then we'll get into the 4 core reasons, the fundamental flaws that make mathematical perfection so tricky for AIs. After we understand the why, we'll get practical and look at how we can get the engineering-grade precision we actually need. And we'll wrap up by looking at what's next, this cool idea called the hybrid approach.
All right, let's dive right into this paradox. It's a bit of a head-scratcher because it goes against everything we think we know about training a model really, really well.
Okay, so just imagine this. You take a simple parabola, nothing fancy. You generate thousands of perfectly clean data points from that equation. You feed it all to your neural network and just let it cook. You watch that error just plummet towards zero. The model has essentially memorized your data set. But then, you ask it for a value, and the answer it gives back is off by some tiny, infuriating little decimal. What gives?
Well, the answer isn't in your code or your model architecture. The problem is way deeper. It comes down to 4 fundamental flaws in the very way these systems work. It's not you, it's the machine. So let's break them down.
Here they are, the 4 culprits. It starts with the numbers themselves, inside the computer. Then it goes to the basic structure of the AI. After that, it's about how it learns from data points. And finally, it's the training process itself. Let's dig into each one. First up, floating point math. So, most AIs are built using 32-bit numbers, what we call float 32. And the key thing to get here is that these numbers aren't perfect. They can only handle about 7 decimal places of precision. That means every single calculation, every multiplication, every addition, it introduces a microscopic rounding error. And those tiny errors, they add up. So right from the get-go, our AI is working with slightly fuzzy numbers.
Flaw number 2 is that a neural network isn't actually doing algebra. It's a function approximator. The best analogy is a master painter trying to copy a photograph. The painting can be breathtakingly realistic, almost perfect, but it's still made of paint and brushstrokes. It's not the photograph. In the same way, a neural network creates a beautiful imitation of our parabola using weights and activation functions, but it never becomes the true mathematical equation.
Third, sampling limitations. This goes hand in hand with that imitation idea. When we overfit the model, we're basically turning it into a world champion at connect the dots. It knows exactly where every single one of our training points is, but here's the catch. It has no real clue what the curve is supposed to look like between those dots. It's just making a really, really good guess based on the points it memorized. And finally, we have the optimizer. Think of training like rolling a ball down a hill to find the lowest point. The optimizer, our training algorithm, is just trying to find a really low spot. It's not trying to find the absolute mathematically perfect bottom. So if the perfect weight is exactly 2.0, the optimizer might land on 2.000000119 and say, yep, close enough. So when you add it all up, fuzzy numbers, an imitation structure, connect the dots learning, and a good enough optimizer, you start to see why true perfection is basically impossible. Okay, so perfect is off the table. That might sound like a downer, but here's the thing. In the real world, we almost never need absolute mathematical perfection. What we need is precision that's good enough for the job. And this is where we get into what we can call engineering-grade precision. In super demanding fields, think CAD, advanced manufacturing, CNC machining, the tolerances are incredibly tight. But they're not infinite. A precision of 1e minus 7, which is 1 part in 10 million, is often the gold standard. In fact, that's even better than what most high-end hardware requires. And the best part? This is totally achievable. So how do we get there? What's the secret sauce? It's actually pretty simple. 3 things. Number 1, and this is the big one, use float 64, or double precision numbers. Just do it. 2, keep your network simple, and use a nice smooth activation function like tan. And 3, if you really want to crush it, You can use special networks, like polynomial networks, that are designed from the ground up to handle this kind of math.
I mean, just look at this table. It tells the whole story. With float 32, you're getting about 7 digits of precision. But when you jump to float 64, bam, you're up to 15 or 16 digits. This simple switch gives your model so much more room to breathe numerically, and it slashes all those little rounding errors we were talking about. And get this, with that setup, just using float 64 and a simple network, you're not just going to hit that 187 target, you're going to blow right past it. It's pretty common to see precision in the range of 1E8 to 1E10, and that is way more than enough for pretty much any engineering task you can throw at it.
And hey, don't just take my word for it. Here's the proof. These are real results. Look at that max absolute error. We're talking 10 to the minus 13. That's an absurdly small number. It's thousands of times more precise than our engineering standard. So yeah, the goal isn't just possible, it's something you can completely dominate.
Okay, so all this talk about a simple parabola is actually pointing to a much bigger, much more important idea. For really complex, mission-critical stuff, maybe trying to get a pure AI to do everything isn't the right move. Maybe the future is actually a hybrid approach. Let's just compare the two. If you go with a pure neural network for something complicated, like building a CAD model from a 3D scan, you're taking a risk. The AI can hallucinate impossible shapes, its precision is tough to guarantee, and it can just fall apart on weird edge cases. And when it breaks, good luck figuring out why. But a hybrid system, it's the best of both worlds. It uses the AI to make a smart guess and then uses a classic, deterministic math kernel to check the work and enforce the rules. It all boils down to this brilliant philosophy. You let the neural network be your creative genius, the perception engine, and the guesser. It looks at the big picture and comes up with a great first draft. But then you bring in the math kernel, the strict, reliable verifier and refiner. It takes that great idea and makes sure it's perfect, robust, and mathematically sound. And so, that really leaves us with this one big question to think about. As we keep building these amazing new tools for engineering and science, our biggest challenge isn't just about making smarter AIs. It's about designing smarter systems that know exactly where to draw that critical line, where AI's incredible but imperfect best guess ends and the timeless absolute guarantee of mathematics begins.